Okay, so what I'd like to talk today about is extending Milnor's U-bar concordance invariance to virtual knots and to welded links. This is based on two papers that are on the archive. So one of them is called Milnor's concordance invariance for knots on surfaces. And the other one, which is joint with Hans Boden, is called Virtual Concordance and the Generalized Alexander Polynomial. All right, let's start with a little motivation about Milnor invariance. So if I take any group G, its lower central series is defined recursively by G1 is equal to G, G2 is equal to the commutator subgroup of G with itself, and GQ plus 1 is the commutator subgroup of GQ with G. And so this defines a series of normal subgroups. Now, if I take a link in the 3-sphere, which has m components, and I let G be the fundamental group of the complement of the link, I'm going to take F to be the free group generated by some meridians of the link. So there's m of those. Then there's this important theorem of Chen and Milnor, which gives you a presentation for the nilpotent quotients of the fundamental group of the link. And so it says that each meridian gives you a generator, and then you have relations which come from the meridians commuting with the longitudes. And so each lambda I to the q here corresponds to the image of a longitude in the qth term of the lower central series. Okay, so what we do then is we take a word in the free group F, and then we write out a power series expansion of it, just using the geometric series power series expansion. So each AI goes to 1 plus AI, and AI inverse goes to 1 minus AI plus AI squared, so on and so forth. And then we just, for any sequence, we take the coefficient of the term corresponding to that sequence. So EJ sub F is AJ1, AJ2, so on and so forth, where J is J1 to JR. And we take the coefficient of that term for each longitude. And so for the kth longitude, we have mu sub J, the last term being the number corresponding to which longitude you want. And then we take the coefficient of that longitude. Then there's an indeterminacy, which is delta sub J, and that's the greatest common divisor of all these coefficients, where we delete at least one term from J or cyclically permute each of those elements. Okay, and the mu-bar invariants are then just defined to be the residue classes of these coefficients modulo the indeterminacy. And so what do we know about these mu-bar concordance invariants? Well, we know lots and lots about them, but just a few things we want to know at the moment are the following. So first of all, they're invariants of link concordance, and this was proved by Casson and Stallings. And we also know that the mu-bar invariants vanish on any boundary links. This was proved by Smythe. So recall that a boundary link is a link in which the components of the link bound pairwise disjoint ciphered surfaces. And lastly, it's easy to show that the mu-bar invariants are all trivial on one component links, or knots. So you can define them for knots, it's just that they're always 0. All right, so what we want to do is to construct an extension of the mu-bar invariants to virtual knots and to knots in thickened surfaces sigma times I, where sigma is closed and oriented. And these are going to be defined from the lower central series of the extended group of a virtual knot. So this is an extension of the usual Wardinger group of a virtual knot. We'll go over what that means in a minute. These will be invariants under virtual concordance in the sense of Turaev, and they vanish on homologically trivial knots in thickened surfaces. So homologically trivial knots sort of being the analog of a boundary link for knots in thickened surfaces. Okay, and we'll have 3 applications of these goals once we accomplish them. So first of all, we'll show that the virtual knot concordance group is not abelian. So that is in contrast to the classical knot concordance group, which we know is abelian. We'll also generalize the mu-bar invariance to welded links, welded string links, and this also works for ribbon torus links in S4 and ribbon tubes. Okay, and we'll also reduce to 4 out of the 92,800 virtual knots from Green's table having unknown slice status. Okay, so let's talk a little bit about virtual concordance. So what is regular concordance? So if we have two knots in the 3-sphere, K and K star, we consider K to be an S3 times 0 and K star to be an S3 times 1. And so we're looking in the product S3 times the interval 0, 1. And if K and K star co-bound a smoothly and properly embedded annulus in S3 times 0, 1, then we say that they are concordant. If you're concordant to the unknot or unlink, you're said to be a slice knot or a slice link. Okay, so what is virtual concordance? So this definition was given by Turaev in 2008. And so it's defined for knots in thickened surfaces. So if you have K is in sigma times I and K star is in sigma star times I, we say they're virtually concordant if there's a 3-manifold W whose boundary is sigma union sigma star. And K and K star co-bound a properly and smoothly embedded annulus in W times I. So here the annulus is denoted by lambda. Okay, so you can also define this for the topological category, and there's some results known about that, but for the moment we'll just be talking about the smooth category. What does virtually slice mean? Any knot in the 3-sphere can be considered as a knot in the thickened 2-sphere, S2 times I. So we'll say that something is virtually slice if you're concordant to the unknot, the usual unknot, considered as a knot in the thickened 2-sphere. Okay, so one nice thing about the definition of virtual concordance is that you can convert it into a combinatorial definition, which is very useful for doing examples. Okay, so let's recall what a virtual knot diagram is. So in a virtual knot diagram, you have an immersed curve in the plane, and instead of just having over and under crossings, you have an additional type of crossing, which is called a virtual crossing. And a virtual crossing is just indicated by a small circle that goes around the double point. Okay, now you can convert any virtual knot diagram to a knot diagram on the surface using what's called the Carter surface construction. Okay, so we start here with just some knot diagram like this. And what we're going to do is we're going to put a 0 handle at each of the classical crossings. We're going to put a 1 handle along each of the edges of the diagram, like so. So the 0 handles here are denoted in green, and then the 1 handles are denoted here in blue. And this gives you a compact oriented surface with some boundary components. And you make this into a closed component just by adding 2 handles along each of the boundary components like this. And so here you get this knot on the left-hand side, this virtual knot on the left-hand side, which has 2 crossings and 1 virtual crossing. And you can draw it on the torus with 2 crossings, and of course you don't need anything else. It's realized as a knot diagram there on the torus. Okay, so there's a way of going back and forth between knots on surfaces and virtual knots. Okay, so virtual knot diagrams are considered up to the extended Reidemeister moves, and so these were defined by Kauffman. So we have the usual Reidemeister moves there on top. We have some additional moves there on the bottom telling you how the virtual crossings interact with each other. And then we have on the right-hand side the move indicating how the virtual crossings interact with the classical crossings. So it's like a virtual Reidemeister 3 move. Okay, so That's virtual knot equivalence. How do you define virtual knot concordance? Well, this definition is due by Kauffman in around 2014. And so the idea is you have saddles and births and deaths, just like you do in regular old classical knot concordance. And you just say two knots are virtually concordant if they're related to each other by these virtual moves, the extended Reidemeister moves, together with births, deaths, and saddles, such that the order characteristic is equal to 0. So the number of births minus the number of saddles plus the number of deaths is equal to 0. There's a nice result by Carter, Kamada, and Satoh in around 2000, which indicates that these are exactly the same. So the two definitions of virtual concordance are equivalent to each other, and at least in the smooth category. All right, so if you have two knots on thickened surfaces, they're going to be virtually concordant if and only if they represent concordant virtual knots. Okay, here's an example of 5, 12, 16 from Green's table. So on the left-hand side, you have a diagram of 5, 12, 16. By the way, this isn't the diagram that's actually in Green's table. This is a different one that just makes it easier to see where the saddle lies. The saddle is indicated there with a blue dashed arc. And if I do the saddle move, I get a two-component virtual link indicated with the two different colors there. And if I do a few Reidemeister moves, I can prove that this is the same thing as the two-component unlink. So if I kill the red component there with the death move, then I get a one-component unknot. We've had one saddle, we've had one death, so the Euler characteristic is 0, and so that means that this knot is concordant to the unknot. Another way of saying it is that this knot is actually a slice. Okay, so here's just some facts about virtual concordance that we know about. So this theorem of Bowden and Nagel from 2017 says that two classical knots in the three-sphere are concordant if and only if they are virtually concordant. So what this means is that virtual knot concordance is a proper extension of classical knot concordance. So another thing that we know, which is similar to the theory of classical knot concordance, is that every virtual knot is concordant to a prime satellite knot, a prime hyperbolic virtual knot, and if the virtual knot is almost classical, it's concordant to a prime satellite AC knot and a prime hyperbolic AC knot having the same Alexander polynomial. So I won't say too much about this, but it just gives you a comparison between the situation for classical knots. Every classical knot we know is concordant to a prime classical knot. That was proved by Kirby and Licorice. It's also concordant to a prime satellite knot. That was proved by Livingston. And Myers showed that every knot is concordant to a prime hyperbolic knot. Of course, hyperbolic implies prime, so we don't need that extra condition. We do need that in the virtual case, however, because there are hyperbolic knots which are not prime in the sense of knot Turaev. And so we have that extra condition to show that a knot is prime. It means that it's prime in the sense of knot Turaev. Okay, so I won't say too much about that, but that's just another comparison of things that are true in both cases. Okay, so slice obstructions. At this point, there's a number of them that are known, so I'll just sort of go through the list from 2008 to 2019. So the first one that we have is due to Turaev, and it's called the graded genus. And then a little bit later, Dye, Kester, and Kauffman extended the Rasmussen invariant to virtual knots and showed that this was a smooth concordance invariant. Then it turned out that a lot of invariants that were already defined were actually invariants under concordance as well. So an example would be the Hendricks-Turaev polynomial, the odd-Rive, the Rive polynomial. These were shown to be concordance invariants later. Rushworth introduced a second kind of Rasmussen invariant and proved that that was an invariant of concordance, and he used it to give some obstructions for sliceness and calculating slicing in some number of cases. Then we also have some things which are only defined for almost classical knots. Those are knots which are admit a homologically trivial representative in some thickened surface. And these are called the directed Tristan-Levine signature functions. They're useful for those almost classical knots. And then most recently, we have the general Alexander polynomial is a slice obstruction also. Okay, so if you just look at the graded genus and the generalized Alexander polynomial, what can you say? Okay, so here's the information from Jeremy Green's table. So we have the crossing number, the number of virtual knots with that crossing number. Then we have what happens when the graded genus is equal to 0, what happens when the graded genus is equal to 0, and the generalized Alexander polynomial are both equal to 0. So up to 6 crossing, there's 92,800 virtual knots. And you'll see how effective the graded genus by itself is. There's, just for the 6 crossing knots, for example, there's 1,476 knots with graded genus equal to 0. Not equal to 0, but the other ones are not equal to 0, so that means we know that they are not sliced. So it's a very effective slice obstruction. Then if you also apply the generalized Alexander polynomial, that reduces it a bit further. Okay, so we get, for example, for 6 crossing, 1,294 knots with both of those being equal to 0. And you can show that, many of those are actually sliced. So there's at least 1,241 which are sliced from 6 crossing knots. And, once you've got that list down, then you can compute some of the other slice obstructions. So the Rasmussen invariants, the directed Tristan-Levine signature functions, and things like that. Okay, and that leaves us with only 38 knots of unknown slice status. Okay, so those knots all have 0 graded genus, 0 generalized Alexander polynomial, trivial Rasmussen invariants, and all of the other known obstructions are vanishing. Okay, so that's just a summary of the calculations done previously. So what can we say now? All right, so here are the knots of unknown slice status. They're listed. So you'll notice we did 5, 12, 16 earlier, so that's a new piece of information. The only other 5 crossing knot of unknown slice status is 1963. Okay, so well, all those knots in there that are red turn out actually to be slice. Okay, so we have slice movies for each of those knots. And so the main issue is just trying to show, determine which of these other ones are sliced or not sliced. And so we'll show that all but 4 of those that are black there have slice obstructions. Okay, so how are these actually defined? So let's talk about the extended mu bar invariance. All right, so the extended group is an extension of the group of a virtual knot. There's many equivalent versions. The first version that I'm aware of is due to Manturov, but Silver and Williams also have a version of this, and Bardakov and Bellingeri have a version of this, and let's see. The version that we're going to use is due to Bowden, Gaudreau, Harper, Nikas, and White. This is because it's the one which is most natural with respect to the Barnett-Tanger construction, which we use to find a geometric realization and prove that these invariants that we're going to construct are invariants of the concordance. So just to make everything clear here, Bowden, Gaudreau, Harper, Nikas, and White refer to this as the reduced virtual knot group. The adjective reduced in the Milnor invariant literature refers to something involving link homotopy. So instead of trying to overuse that adjective, we're just going to refer to these things as all of them as the extended group. And so that's the notation of Silver and Williams, but they're all isomorphic. So we'll just say all of these are extended group to avoid any confusion with the Milnor invariant literature. Okay, so here's how it's defined. For each of the half arcs in the diagram, So that means, if you think of this as just as a graph, you just label all of the edges of the graph by a generator of the group. So for example, on the left-hand side, we have A, B, C, and D. All those correspond to labels of arcs. We have a relation, a pair of relations for each type of crossing. So for a positive crossing, we have VA V inverse is equal to C, and A inverse V inverse B VA is equal to D. The variable V is an auxiliary variable, which is used to define the group. Similar relation for the negative crossing, and then we also have that in virtual crossings, there's essentially no relation. And so the extended group is just defined by these generators together with the auxiliary variable V, together with the pair of relations at each crossing. And you'll notice that this is indeed an extension of the group of a virtual link, because if you just set V equal to 1, you'll have, for example, in the positive crossing, C equals 1, A, 1 inverse. And so that tells you that C equals A, and that recovers the usual Werdinger relation that, there's one label for the overcrossing. For the second relation, we have D equals A inverse V inverse B VA, and if V is equal to 1, then again, you just recover the usual relation from the Werdinger group. Okay, so our theorem here is that these extended groups also have a Chen-Milnor type theorem. So if you have an M component virtual link, you take F to be the free group on M plus 1 letters, A1 to AM, and V is the auxiliary variable. Then the nilpotent quotients of the extended group are given by G tilde mod G tilde Q is isomorphic to, we have one generator for each meridian, we have a generator for the auxiliary variable, and then we have these commutator relations for these the generators and these longitudes. We'll be able to interpret these as longitudes geometrically also, but for the moment, just think of these as words that occur in the nilpotent quotients. Okay, so a corollary of this is that if you apply this to a virtual knot, and F is just the free group of AV. So here A is just a generator of, corresponding to a meridian, and V is the generator corresponding to the auxiliary variable. Then the nilpotent quotients are isomorphic to AV, and you have one relation, which is A lambda tilde Q. So this kind of extended longitude here can be calculated. I'll give an example in a second. And we have a very simple presentation in the case where you have a virtual knot. And so the thing that's different about this is that if you take the nilpotent quotients of the group of a virtual knot, just like in the classical case, those are always going to be isomorphic to the nilpotent quotients of a free group. And so that means you get nothing useful, again, out of the group of a knot. However, if you look at the extended group, the nilpotent quotients are generally not free, and you get interesting invariants. Okay, so now that we have a Chen-Milnor theorem, we just proceed exactly as Milnor did to define invariance of the link. We just write out the minus expansion of that longitude we get from the extended Chen-Milnor theorem, and we just take the coefficients as usual. One thing I'll point out here is that the index here doesn't include the information about which longitude we're using, because for virtual knots, there's only one interesting extended longitude. So we don't need to record each of those. Okay, so when you take these coefficients, we call these the je bar invariance. And so again, I'll tell you what this je means and how it can be interpreted a little bit later. And these are all concordance invariants of virtual knots. All right, let's just do a quick example. of how these are computed. So here is the Gauss diagram of 3.5 from Green's table. That little black dot there indicates the base point that's in Green's table. I've labeled the arcs of the Gauss diagram, and you can read off a presentation of the extended group sort of in the usual way. As you walk along the arcs of the Gauss diagram, you have a relation every time you come to a crossing point. When I go to an overcrossing arc, I'm going to get a relation of the form VA-V inverse, or V inverse AV, corresponding to whether that's a positive or negative crossing. When I go through an undercrossing, I use the other relation for the extended group. And so you'll see here as I go across from the base point, going around the diagram, I first cross each of the overcrossings, giving me a relation of type VA-V inverse, or V inverse AV. And then as I go around back to the base point, I go through each of the undercrossings where I use the other relation. And from this, you can read off a longitude exactly in the usual way. There's no difference whatsoever in the algorithm. And then what you do is you calculate its image in the nilpotent quotient. So for our case, up to order 3, all the longitudes are trivial. So we're going to look at the invariance of order, which means we have to calculate the 4th longitude. So you just do that in the usual way. That's what it's equal to for 3.5. Now, to compute the J-bar invariance, we have to then write out these longitudes are the product of commutators. There's an algorithm for doing this. For example, the famous one is Hall's basis theorem. There's other versions of this, but that's the one I use for this particular calculation. And then once you've written in that nice way, then you can use the properties of the Magnus expansion coefficients to calculate these invariants recursively. Okay, and so here I have all possible sequences J for order 3 and their corresponding Magnus expansion coefficients. There's 8 of them and 8 J's, and so that gives you, possibly different values. And you'll notice here that there's lots of patterns here. So you have 4s and 8s kind of showing up in not random seeming way, and that's true. There's lots of relations between these invariants. Here we're just showing all of them. Later we'll just show a spanning set of invariants. Okay, so here are a few properties of these J-bar invariants. So first of all, recall that a virtual knot is said to be almost classical if it emits a homologically trivial representative in some thickened surface. So that just means it bounds a ciphered surface in some thickened surface. First thing to know is that if you have a knot which is concordant to any almost classical knot, then the J-bar invariants are automatically equal to 0. And so that means that the J-bar invariants really are obstructions to being concordant to an almost classical knot. In particular, they are obstructions to being a slice. Okay, so another property is that if you have a virtual knot and all of its J-bar invariants are vanishing for all sequences, then that implies that the generalized Alexander polynomial of K is trivial. And by a theorem of Meller, we know that the generalized Alexander polynomial determines the odd-Rive, Heinrich-Turaev polynomial, affine-index polynomial, or Rive polynomial. So that means that whenever the J-bar invariants are 0 for all sequences J, then the odd-Rive, Heinrich-Turaev polynomial, and affine-index, or Rive polynomial, are all themselves trivial. And so what that means is the J-bar invariants are at least as strong as that family of slice obstructions that come from the generalized Alexander polynomial. But on the other hand, it can also be stronger. Okay, so let's go back and look at some of those knots that were on the unknown list. They're listed here on the left-hand side with their Gauss codes. I'm not going to write out their longitudes because even when they're reduced, some of them can be quite long. So for example, you see one there that has a longitude length 1120. Some of them are shorter than others, and you can actually do the calculations by hand, but we've done this with a computer. So Mathematica is used to actually write out the word and the nilpotent quotient, and then we use a program in GAP, which is called A and U in Q, to compute the Hall basis. So writing out as a product of commutators. And that is given there on the right-hand side. So that is the basis for the nilpotent quotient given by GAP. Okay, so let me tell you what those G10, G11, G12, G13 actually are. So the commutator basis used by A and U and Q is G1 is equal to A, G2 is equal to V. And then you have, as the depth of the commutator increases, you have these different sort of commutators. These are all left bracketed commutators, which means that, for example, G4, which is VAA, is really the commutator of V with A, again, commutated with A. And so you bracket all the commutators to the left. All right, so once you've used GAP to compute these product of commutators, then you can just use the properties of the mass expansion to calculate the j-bar invariance. And so here we have a list of the invariants of order 5. All the invariants of order 4 are 0. So these are the first non-vanishing invariants. This particular list here is a spanning set of invariants. So all of the invariants of order 5 can be written as a linear combination of those 6 invariants. Okay? And so here they are calculated for each of the knots shown in the previous slide. And you'll see that at least one of the j-bar invariants is non-vanishing from this spanning set of invariants. And so therefore, each of these knots is not sluts. Okay, so you can also get some interesting results by looking at the invariants beyond the first non-vanishing degree. So for example, here's 419 and 432. These two knots have the same generalized Alexander polynomial. And so in particular, that means they have the same odd-Rive, Heinrich-Rive polynomial, and affine index polynomial. They also have the same graded genus and the same slice genus. They also have the same j-bar invariance up to degree 3. However, you can compute the invariance up to degree 4. They're listed there at the bottom of the screen. And you can see that they don't agree identically. So that means that these two things are not concordant to one another. Okay, so let's talk about our second application for a little bit, the virtual knot concordance group. So here we have two long virtual knots. So a long virtual knot is just a long knot where we allow both classical and virtual crossings. Here we're giving 2.1 and 3.1 exactly the words from as they appear from Green's table. And in concatenation, we just take one of the knots and we continue on with the other knot. So 2.1 concatenated with 3.1 looks like the diagram on the bottom of the screen. Okay, so you can define this virtual concordance group, same definition of concordance used for the for the round case. We have that the elements are concordance classes of long virtual knots. The operation is concatenation, and then the long unknot is the unit. And so if you reinterpret the Boden-Nagel theorem that we previously discussed, this just shows that the classical knot concordance group embeds in the virtual knot concordance group. Okay, so Turaev was the first person to really look at these kinds of things in his paper, Cobordisms of Knots on Surfaces. And the last sentence of that paper is it abelian? So he asked whether or not this group is actually commutative. So around the same time, Mantorov showed that equivalence classes of long virtual knots form a non-commutative monoid. So that gives some positive evidence to the fact that this might not actually be abelian. But under concordance, that's a much more coarse relation, so it's a little bit more involved. Okay, so you can define an extended group for long virtual knots in the usual way. It's a little bit different, but it's the same, exact definition, same relations at each of the classical and virtual crossings, and its extended Chen-Milnor theorem looks a little bit different. So if you have a virtual knot, F is a free group on two letters AV, then in this case, the nilpotent quotients of the extended group are always isomorphic to those of a free group. And so that means that to construct concordance invariance, you have to do something a little bit more than just looking at the Magnus expansion. Okay, so what we're going to do is follow Haber-Len, who looked at this for string lengths in the classical case. We're going to construct a map going from the long virtual knot concordance group to the automorphism group on the free group two letters modulo its lower central series. And so for each long knot K, that map is defined as follows. So you send the auxiliary variable to itself, and then the map acts on A by conjugating with the extended longitude. Okay, so this turns out to be a concordance invariant of long virtual knots. Okay, and so using this, you can show that the long virtual knot concordance group is not abelian. And so the idea is, well, you can just actually calculate these concordance invariants in different cases. And so you just show that the value of 2.1 times 3.1 is not the same thing as 3.1 times 2.1. So you have to go out all the way to the 8th term to make the 8th Artin representation to make that actually work, but you can actually do the calculation. Okay, and a corollary of this is there exists non-concordant long virtual knots having concordant closure. Because 2.1 times 3.1 has the same closure as 3.1 times 2.1. Okay, so you can also use this to obstruct sliceness for some round virtual knots where the usual J-bar invariants are 0 out to a very high order. So here we have 6.8451, and you'll notice that this can be viewed as a product of two knots. So here we have two little knots glued together to make a bigger knot. And to show that it's not sliced, we just have to show that one of those knots is not the concordance inverse of the other knot in the long virtual knot concordance group. Okay, and that actually works in this particular case. The calculation is in the first paper listed at the beginning of the talk. All right, and so that leaves only 4 knots of unknown slice status. Those 4 knots there. I have calculated them out to relatively high order, and all the variants that I can calculate are 0. But of course, it's possible that if one calculated them out to higher order, they would be non-vanishing. Okay, so let's talk for a few minutes about why this is actually true. All right, so here's an outline of the proof. So here, je stands for Barnatan-je map. I'm going to define that in a second. And tube stands for Satoh's tube map. All right, so first what we do is we have a geometric realization. So this je map is a map that goes from virtual knots to welded links. And the tube map goes from welded links to ribbon torus links in S4. And so the interesting thing about these maps is that they induce isomorphisms on the corresponding groups. So the extended group of K is isomorphic to the usual knot group of the two-component link j of K. And that is in turn isomorphic to the fundamental group of the complement of the ribbon torus link tube of j of K. Now, this j map turns out to be functorial under concordance. And also the tube map is functorial under concordance. And so the idea is that we just take the mu bar concordance invariants of ribbon torus links, or you can also think that as welded links because the isomorphisms they turn out to be the same. And you just compose them all together. So you take a knot, you apply j to get a two-component welded link, you apply tube to get a ribbon torus link, and then those Milnor invariants give you the j bar invariants. All of those things are either functorial or invariant under concordance, and so you get new concordance invariants of virtual. Okay, so let's remind ourselves what we mean by welded knots. So welded knots are virtual knots up to the same relations as before, so the extended Reidemeister moves, together with the operation overcrossings commute. Concordance of welded knots is defined the same way. All we're doing is just adding this new relation, overcrossings commute. So it just means you can always reorder any arc containing only overcrossings to any other arc also containing all overcrossings. Okay, so now we're ready to define the j map. All right, so what we're going to do is we're going to add a new component to any knot. So I start with my knot diagram, in this case a virtual knot diagram, and I'm going to add a new component as follows. So at each crossing, I have two little blue arcs. The one, goes over the overcrossing arc, and then it goes over the undercrossing arc is indicated there. I can also do it on the other way. Those are equivalent by a Reidemeister 2 move. And after I've done this at every crossing, I just I connect all of those little blue arcs together in an arbitrary fashion. If I have to make any new crossings during the connection process, I mark those as virtual crossings. This turns out to be well defined because of this overcrossings commute relation. Okay. I'll point out also, we really don't need to consider them to be welded links. We can really consider these to be what are called semi-welded links. And that means that we only require the overcrossing arc, the overcrossings commute relation on the omega component. The omega component being the new component which is added to the link diagram. Okay, so here's just an example. Here is the virtual trefoil, and we add the blue omega component as follows. The dotted arcs just indicate our particular choice for connecting the edges together. We could have chosen any other ordering. It will give you the same thing up to semi-welded equivalents. Whenever the blue arcs cross over the original arc, those new crossings are marked with virtual crossings. All right, so this is an invariant under the Reidemeister move. So here's just a quick proof of that. And this was originally proved by Barnatan in some talks that he gave at Moscow State University and McMaster University. There's a link in the paper to those talks, and we wrote out some more details of the proof in that paper. Okay. All right, so besides being well-defined and invariant of the Reidemeister moves, it also is a concordance invariant. And so that's kind of easy to see if you think about it, because well, concordance doesn't involve any crossings whatsoever. So the birth, death, and saddle relations are not affected by, they don't introduce any new crossing, right? So as a result, when you apply the je map to concordant links, nothing unusual happens, and you get a concordance of those semi-welded links. Okay, so this fact was also observed by Artin, that the extended group of K is isomorphic to the group of je of K. And we've written out a little proof down there at the bottom. And the idea is that if you take the usual presentation of the group of je of K, then it collapses to the presentation for the extended group of K. So in my picture here, I've just written out the relations of the group of je of K. And so if you stare at that for a little bit, you'll see that that is identical to the presentation for the extended group of K. And so that's useful because it gives you a geometric interpretation of the extended group of K. It says that the extended group of K is just the usual group of je of K. Okay, so the second ingredient is Satoh's tube map. And so what does the tube map do? So first of all, let's recall the idea of a broken surface diagram. So if I have a knot in S4, I can draw it as a immersed surface in R3. And along each double line, I draw it as a broken surface diagram by breaking along the lower coordinate. So if I have, let's say, the map which defines the projection is just R4 going to R3, where the fourth coordinate is mapped to nothing, right? So it's the identity on the first three coordinates, and it projects the fourth coordinate to nothing. Then the map just defines the broken surface diagram just says that the sheet that has the smaller R4 coordinate is drawn as broken, as depicted there in the right-hand side. So that's the same convention that we use, say, for classical knot diagrams. Right? In that case, we have R3 going to R2 instead of R4 going to R3. All right, so how is the tube map defined? So if I have a welded link diagram, I make the broken surface diagram corresponding to that welded link as follows. So along any of the arcs of the diagram, I replace it with an annulus. If I have a classical crossing, I have a annulus which passes through the other annulus as depicted there. And then at a virtual crossing, I have one of the tubes just overcrosses the other tube. It doesn't matter which way that you do it. You can have it the other tube going over say the horizontal tube as well. That's totally fine. Those are equivalent up to isotopy. Okay, so Satoh proved that if you have two equivalent welded links, then their tubes are isotopic in S4. And he also proved that if you take the group of a welded link, so that's the group defined with the usual Werninger presentation, that is isomorphic to the complement of the fundamental group of the complement of tube of L in S4. Okay, and so what do we mean by concordance of torus links, ribbon torus links? So a concordance of ribbon torus links is just a smooth and proper embedding W into S4 times I. Each component is diffeomorphic to S1 times I. and the intersection of W with S4 times little I is equal to Ti. So it's the same definition that you have for classical link concordance. It's just that the manifold in between T0 and T1 is S1 times S1 times I rather than just the annulus S1 times I. And so it turns out that if you have two concordant welded links, then their tubes are also concordant to each other. And so this argument is just a handle decomposition argument. I won't go over it in the interest of time, but you can look it up if you like. Okay, so back to our main problem of determining how the J-bar invariants are invariant under concordance. And so first lemma is that if you have two welded links and you have a concordance between their tubes, then the nilpotent quotients of the fundamental groups of the complement of the tubes are isomorphic to each other and isomorphic to the complement of the concordance in S4 times I. And if you apply that together with the isomorphisms that Satoh found, that shows that the nilpotent quotients of the group of the link L are isomorphic to the nilpotent quotients of the group of the link L star. Now, the important thing about this is that these isomorphisms all preserve the longitudes. So if I start with a longitude of any component of the link L, then following these isomorphisms all through, they are actually preserved. Here, the Q sub Q of A denotes the Qth nilpotent quotient of the group A. Okay, now how do you prove this? Well, it's really just Stalling's theorem. So it's a similar argument that is used to prove that the Milnor invariants of classical links are invariants under concordance. Okay, and so as a consequence of this, we find that if you have two welded concordant virtual links, or you can rephrase this as concordant ribbon torus links in S4, it's the same definition, then for all sequences J of length at least 2, then their mu bar invariants are the same up to the usual indeterminacy. Okay, so I'll just pause for a second here to talk about some other types of Milnor invariants which have been talked about for welded links. So Dye and Kauffman defined a version of link homotopy invariants. And then Odu, Bellingeri, Milham, and Wagner also looked at link homotopy invariants using a construction, also using the tube map. Some other results on link homotopy invariants were given by Kurchenko and Polyak, and also Katori. And Katori's approach uses nano words. It's a different kind of way of thinking about it. And very recently, Miyazawa, Wada, and Yashihara looked at link isotopy invariants. So these are the same invariants that we're talking about here. They looked at it just in the case of link isotopy, and here we're proving it using their invariance of concordance. Our argument here is geometric, and their argument is more combinatorial. So that's an interesting paper you should also look at. Okay, so if we put all of this stuff together, what do we have? So recall that each of our interesting maps is functorial under concordance. So we have the Je map, which goes from virtual knots to two-component semi-welded links. We have the tube map, which goes from welded links to ribbon torus links in S4. The Je bar invariants are just the mu bar invariants composed with the Je map. Okay, and so all of that concordance, all of those are functorial under concordance, and so that means that the Je bar invariants are themselves functorial under concordance. Okay, and so that's the end of the proof. And that's all we have to say. So thank you very much for listening to this talk.